All right, so our goal with each of these examples is to determine the domain and range of the relation, and also to decide whether or not the relation is a function. Okay, so let's start with our green guy up here. This is known as a discrete list, right? It just has a list of ordered pairs. Now, in our ordered pairs, remember that the domain is the number that comes first. So our domain will consist of 1, 4, 9, 9 again. Now I already have 9. Do I need to write it again? Nah. 4, that's already in my list, and 1. So it turns out our domain here is just 1, 4, and 9. Our range, remember, is all of the things that come in the second position, or our y values. So it'll be 1, 2, 3, 1, 2, 3, -3, -2, and -1. Okay? So there's our domain and range. Domain, things that come in the first position. We're probably starting to notice that those are our x values. Range, things that come in the second position of a relation, are y values. And the other thing we wanted to know is we wanted to know whether or not this relation, t, was a function. In order to be a function, every domain element has to map to a unique range element. So what do you think, function or not? Yeah, this is definitely not a function. It fails several times, right? 1 goes to 1, but 1 is also mapping to -1. 4 is going to both 2 and -2. 9 is going to both 9 and 9 is going to both 3 and -3. So this is not a function. Okay, so let's look at our next one. Here we have a table of x and y values. Okay? We could think of these, if you prefer, as ordered pairs, right? -2, 3 is the ordered pair, -2, -3, -1, -1, 0, 1, 1, 3, 2, 5. Okay, so this is very similar to our list of ordered pairs here, just a slightly different way of thinking about it. And our domain will be all of our x values, so it's pretty easy to pick up our domain here. It'll be -2, -1, 0, 1, 2. Our range will be all of our y values. So that will be -3, -1, 1, 3, and 5. Now let's answer the question, is this a function? Is this a function? Well, in order to be a function, all of our x values have to map to unique y values, or our x values can't do double duty. Well, I don't have a repeated x value, so this is a function. In other words, no x value is going to 2 distinct y values. All right, here's where it starts to get really fun. This is still a relation. Now this is a graph, right? But it's also a relation. Remember what a relation does. A relation relates two things together, x values and y values for most cases in math. So how is this relating x and y values together? Well, any point I pick on this circle has an x value and a y value. So for example, this point up here, this is the point 0, 3. So that says 0 is mapping to 3. Similarly, this point here is the point -2, 0. That says -2 is mapping to 0. This point down here is the point 0, -2. 0, -2. So 0 is mapping to -2, etc. Now there are lots of other points on the circle, right? I could try and figure out what this point is, what this point is, what this point is, what this point is. In other words, there are infinitely many points on the circle that are part of the relation defined by this graph. Now, what that means is we're going to have to think about our domain and range a little bit differently. Okay? So remember that in general, our domain are all of the elements in the first set. Elements, or things, in first set. Now for us, right, when we're thinking about ordered pairs, things in the first set are our x values. So it's very common for us to think of domain as our x values. Okay? Now our x-axis is our horizontal axis. So one way of thinking about our domain is it's asking us which of these numbers along the x-axis are a part of this graph. Well, is -3 right out here, is that a part of this graph? No. How do I know? Because if I go up or down, I don't actually hit my circle. I don't actually hit my graph. Okay? What about, say, -1? Well, -1 is this point right here would have x value -1. Turns out so would this point down here. So -1 is a part of my graph. So is -1/2, and -1/4, and +1/2, and +3/4. There are infinitely many x values that are a part of this graph. Okay? In fact, I'm going to make the claim that all of the x values between -2 and 2 are a part of this graph. Can you see that by looking at the graph? I pick along this red line, I'm going to go up or down and hit function. Outside of that red line, there's no function. Sorry, I keep saying function, and we don't know for sure that this is a function. I should use the term graph, right? Only the part of the x-axis that's covered by this red line is a part of our graph, okay? That means our domain is going to be given by this red line. But think back to what we did with interval notation and number lines. Can I write this interval? This is the interval from -2 to 2. Okay, so from -2 to 2. So this says from -2 to 2. Good, that's good. Now what about the endpoints? Are we going to include -2? Well, yeah, -2 is certainly part of our graph. What about 2? 2 is also part of our graph. When something is included, we use the brackets. So our domain says everything from -2 to 2, all x values between -2 to 2, including -2 and including 2. Let's see if we can't do something similar for our range. Okay. Now our range, remember, is elements in the second set. In this case, in general, we can think of our range then as our y values. Okay. So for example, 3 is a part of our range, 0 is a part of our range, -2 is a part of our range. Those are all y values that are included on this graph. Okay. Now our y-axis is our vertical axis. So we're going to figure out our range by looking at our vertical axis. So down here at -3, I don't have any graph. So -3 is not a part of my range. Where do I start having graph? I start having graph right here at -2, and I continue to have graph. If I go left or right, I hit graph. I continue to have graph all the way up to 3. So this blue line is going to define our range. Now, can we write that blue line as an interval? I think we can. This is all the y values from -2 up to 3. So we would say from -2 up to 3. Okay. In this case, we would include -2. It's certainly part of our graph, and we would include 3. So our range is all y values -2 to 3, including -2 and including 3. Okay. Notice the difference between our domain and range in these first two examples and our domain and range here. Our domain and range for these first two examples, the green and the purple, are discrete lists, meaning there's a finite number of domain and range elements. Here, there's only 3 domain elements, 1, 2, 3. I can count them, I can list them. Here, there's only 1, 2, 3, 4, 5 domain elements. These are what are known as discrete. We have to do our domain and range here as an infinite list or an interval because we simply can't list everything. If I tried to list everything in my domain, I would be listing forever because say 1/2, 1/3, 1/4, 1/5, 1/6, 1/7, all of those are part of my domain. I can make that list go on forever. Instead, we use an interval, which allows us to, instead of listing all of the values, describe them. This says everything between -2 and 2. I can't list those, but I can use that description to describe it, okay? All right, so last thing we need to do is we need to decide if this orange graph is a function or not. Whew, what is a function? Oh yes, a function is something where every domain element, that is all of our x values, are mapping to unique y values. I can't have any x values doing double duty. Is this a function? Well, look at the points that I have labeled here, 0, 3, and 0, -2. Isn't that the same x value, 0, doing double duty? 0 is pairing with 3, and 0 is pairing with -2. That's not okay if you're going to be a function. So this is not a function. Now, some of you may remember the vertical line test, okay? The vertical line test is a quick and easy way to see if a graph is a function. The vertical line test says if you can draw a vertical line straight up and down anywhere through your graph and it passes through 2 or more points of your graph, that graph is not a function. We say this circle fails the vertical line test because what does the vertical line test tell us? It literally tells us that this domain value is doing double duty. It's mapping here and here. Okay, so if a graph fails the vertical line test, it is not a function. All right, I'm going to put up a couple more examples for us to look at. All right, so a couple more examples. All of these are relations. We're going to consider the domain and range and also think about whether or not these are functions. Okay, all right. So this is what's known as a domain and range map. Notice that it has the domain here, the range here. Okay, so the nice thing about domain and range maps, it's really easy to figure out the domain. Here it is. The domain is 5, 7, 9, and 3. I feel almost silly writing it, but I'm going to. The domain is 5, 7, 9, and 3. And the range is -1, -2, -4, -5. Again, these are discrete domains. and ranges, meaning there's a finite number of them as opposed to an infinite number. There's only 4 elements of the domain, 4 elements of the range. I use a discrete list, curly brackets, in order to list them. Now let's try and answer the question whether or not this is a function. In order to be a function, each element of the domain has to map to a unique element of the range. Okay? So let's consider this. 5 is mapping to -1. 7 is also mapping to -1. Is that okay? That is okay, right? Doesn't say that range elements have to be unique. That's something known as one-to-one. We'll get to that in chapter 6. For us to be a function, each element of the domain has to map to a unique element of the range, meaning domain elements can't do double duty. 5 and 7 can both go to -1. That's fine. However, we do have a problem right here. Notice that 9 is doing double duty. 9 is mapping to -2, and 9 is also mapping to -4. That's a problem. This domain element is doing double duty, thus this is not a function. All right, let's look at our other examples over here. These are, again, graphs, so they're drawn on the board. Okay. Now, let's think about domain and range, and then answer the question, are these functions? So when I'm thinking about the domain of this graph, remember that our domain is our x values. Okay? So all the x values that are a part of this graph. Well, I can pick out some x values that are part of this graph. For example, 2 is a part of the graph because this point right here would have x value 2. 1, 2, 3, 4 is a part of this graph because this value here would have x value 4. Now, unlike over here where I could make a discrete list, 5, 7, 9, 3, I can't simply list all of the possible x values. Why? Because there are infinitely many of them, and I can't make a list that has infinitely many things on them. I'd be writing forever, okay? Instead, we're going to use interval notation to describe our domain. So where does our domain start? With domain, we're going to work from left to right, or smallest to largest, negative to positive, however you want to think about that. So I'm going to think, okay, I don't have any domain over here. Where do I start having x values? Well, I start having x values right here, and I continue having x values forever, right? Because that's what these arrows mean. These arrows mean that this graph continues on forever, okay? So let's think about our domain in terms of an interval. Our domain is going to start at 0 and go forever, okay? So all numbers from 0 to infinity, all positive numbers. Let's think about our endpoints. Is 0 included? Yeah, 0 is a point on the graph. X equals 0 is right there. What about infinity? Well, remember, we never include infinity, okay? So our domain is bracket 0, comma, infinity, which is 0 to infinity, including 0. Now let's think about our range, okay? Remember that our range is going to be all the included y values. All right, so remember that when a graph has these arrows, that means the graph continues on for forever. So this graph is going to continue on forever, and as it does that, it's going to get wider and wider and wider. What does that mean? Well, that means eventually this piece is going to go down, and it'll eventually cover all of the negative y values. This piece will keep getting bigger and taller and taller and taller. It'll eventually cover all of the positive y values. So it seems like our range is just going to be everything. Eventually, every y value is going to be covered in that graph. So our range is all the numbers. How do I write all the numbers as an interval? Well, if I think infinity-wise, this is going to start at negative infinity and go all the way into positive infinity. That's how we say all the things. Negative infinity to positive infinity. Now remember, we always use parentheses with infinity, so this is everything, all real numbers. All right, let's answer the question, is this a function? What do you think? I think no. Remember, we talked briefly about that idea of the vertical line test. Vertical line test, which I often abbreviate the VLT. Sounds like a delicious sandwich without the bacon, okay? The vertical line test, right, basically says if a vertical line, straight up and down, drawn anywhere on the graph, passes through 2 or more points of the function, sorry, points of the graph. We don't know if it's a function. Okay. Then the graph fails to be a function. Okay, so the vertical line test is a shortcut for that function definition. If I can draw a vertical line anywhere at all, so for example, oh, I drew a vertical line right there, and that vertical line passes through the function once, twice. That means that this graph fails the vertical line test, and it is not a function. That vertical line test is a shortcut for telling us that this x value, 1, 2, 3, is doing double duty, because 3 is matched up here somewhere with maybe 2-ish, and down here somewhere with -3. I'm just guessing at those values. But either way, the x value 3 is matching with 2 y values, or that x value is doing double duty. That's not the only one that's doing double duty. In fact, all x values in this particular graph are doing double duty. It only takes one to fail to be a function. Let's look at this graph down here. Let's do our domain, our range, and decide whether or not this is a function. Okay, so remember that our domain is our x values. We're going to do our domain as an interval notation. Well, I certainly don't have any graph over here, so no x values over here. I think it's helpful to draw a little line that shows which x values are included in this graph. And that line would look like this. In other words, all of the x values highlighted on this red line are going to be a part of this graph. Then the question becomes, how do I write an interval for this red line? Remember, when we do intervals, we always work from left to right. So this arrow tells me this line is going to keep going to -infinity. So my domain is going to start at -infinity, and it's going to stop right there at 1, 2, 3, -4. So our domain is -infinity to -4. We never include infinities. And we're going to include -4 because look at that solid circle right there. Okay, so our domain is -infinity to -4. How about our range? Well, remember our range is our y values, or we're thinking about the vertical values. So again, I'm going to draw a line that shows all of the vertical values that are included. Okay? There's no graph up here, so I'm not going to draw my blue line here. I start having graph here, and then again, this arrow tells me that this continues on forever. It looks like it's flattening out, but it's really not. It's going to continue on forever and ever and ever. That means our range, again, we work bottom to top, is going to start at -infinity. This arrow tells me it goes on forever, and stop at 1. I never include infinity. I'm going to include 1. So our range is -infinity to 1. Last, is this a function? Well, remember we have this vertical line test. The vertical line test says if I can draw a vertical line anywhere and it passes through 2 or more points of the function, not a function, 2 or more points of the graph. In this case, if I think of my marker as my vertical line, is that ever going to pass through the function twice? It's not, which means yes, this guy is in fact a function. Okay, so that's functions versus relations, domain, and range. Whew, good job, guys.